I'm Ashley Gore.
And I'm Joey Vangsness.
And this is Physics. We're here to talk to you today about horizontal motion in one dimension.
Not one direction.
Here's Allie with the variables.
Hi, I'm here to tell you about the variables. T, time. V, velocity. V naught, initial velocity. Delta X, distance. Acceleration.
So we've got displacement, which is the distance, but it's a vector quantity. Initial velocity, meters per second, it's speed with a direction. Final velocity, again, it's the last velocity we have in our model. Acceleration, if it's positive, it's increasing. If it's negative, it's decelerating. And then finally, we've got time. So if something's decelerating, it's losing speed or losing the velocity as time increases.
Here's a message from our sponsors.
So here's our equation. Now let's look at the units. Well, the units for displacement is meters. So meters for displacement, just like normal. Then we have the unit for acceleration, which is still meters per second squared or meters per second. So those are still the same. The unit for time is also the same, okay? Seconds for time. But be careful in this equation. Like I mentioned, it's getting squared. So it's seconds squared. So we end up with something that looks like this for that variable or that part of the equation. Well, this second squared in time squared is being multiplied by the acceleration. So you get meters per second squared times second squared. And what's going to happen is that's going to cancel with the acceleration unit. And we're going to get those seconds squared canceling, and we're left with meters, which is good because this equation in this form is solving for displacement. So we want our final unit over here to be meters, which it is because this second squared cancels with the meters per second squared to give us those meters.
Back to Ashley in the field with your equations.
Hey everyone, I'm out here in the field. It's a nice day out. We've got some equations for you here that'll solve any problem with horizontal motion in one dimension. We've got velocity equals starting velocity plus acceleration times time. We've got distance equals 1/2 times the quantity of starting velocity plus velocity times time. We've got velocity squared equals starting velocity squared plus 2 times acceleration times the distance. And last but certainly not least, we have distance equals, whoa, it's getting a little windy out. We've got distance equals starting velocity times time plus 1/2 acceleration t squared. Take it back to Joey.
Breaking news, scientists have just discovered a brand new method of figuring out equations. It's called the guess method. You just use the given, the unknown, the equation, and you substitute, and finally you solve.
Here's Ashley with the traffic update.
Breaking news. Steve is approaching a stoplight with a velocity of 30 meters per second. The light turns yellow and Steve applies the brakes and skids to a stop. If Steve's acceleration is -8 meters per second squared, then determine the displacement of the car during the skidding process.
Equation VF squared equals VI squared plus 2AD. Let's list the players over here. Initial velocity was 30 meters per second. The final velocity was a stop. At stopping, you have no velocity. We saw that acceleration was -8 meters per second squared. We wanted to find out what displacement was, and time was actually not even mentioned here, so it's not applicable to us. At this point, it's known as plug and chug. I want you to plug the numbers in, and we're going to start solving the problem. Feel free to press pause and see if you can solve this problem on your own. I'm going to work right through it, though. So we have 0 meters per second as my final velocity, and that's going to be squared. And I think you can see that's going to be 0. We have the initial velocity of 30 meters per second. That too is going to be squared. We're going to be multiplying that by 2 times the acceleration, -8 meters per second squared, times the displacement. Let's start crunching numbers here. Alright, this is obviously going to stay 0 meters per second. I squared it, so I squared the variables as well. I have 30 meters per second. I'm going to square that, and that's going to make 900 meters per second, and they're both squared because I squared them. Plus 2 times -8, which is going to give us -16 meters per second squared, multiplied by the displacement. Alright, crucial point here. In order to solve this problem, which is looking for displacement, you need to isolate displacement. And what I mean by that is that, I'm going to bring this right up here, guys. You need something that says displacement equals. You have to get it alone. In order to get it alone, we first need to address the 900. We need to subtract out 900 from this side as well as this side. And when I do that, I end up with -900 meters squared, second squared, is equal to -16 meters per second squared times the displacement. Next, I still have to go a little further. Let's isolate displacement by dividing out by -16. And when I divide out by -16, I have -900 divided by -16 meters per second squared is going to be equal to what I'm looking for before, isolating my displacement.
This has been the 5th period news. Thanks for tuning in.
Stick.
I'm gonna let y'all finish, but the greatest horizontal kinematics film ever made was made by us three.
Stay positive.